I'm not one of those people that stand up there. You'll run into them. I try not to. Yeah. I never could stand when someone asks a question. And it's one thing to, like a physiology class, to say, I never thought of it that way. And all you'll see me do is, let's work through the physiology together. Like how, because you don't exactly know. Then you got some people who just start spewing stuff out, and I call I'm like, and everybody in the room knows they really don't know, but they're saying it like they do. And everybody else has got Wikipedia pulled up while they're doing it, going, he's wrong. So when I know, I actually don't believe Wikipedia. In other words, I'm not going to attack it for it. I don't know, I'll tell you I don't know. If it's a good enough question, I'll go look it up. Same as you'll do as a clinician. Okay. Tissues. So I put in here this block so we can get the I like to do overalls in a lot of things. If you haven't noticed, you will notice. And then we get into detail. Some people like that, some people don't. Some people want it all at once. So the last part of the material for test 1 is like an introduction to tissues and how they're connected and what are the basic types. And the next block, test 2, is all tissues. We're going to study cutaneous layers, muscle tissue in detail, like down to the cellular level. But here we're just going to get kind of an overview. And so if you look at tissues and you were to go back and study embryology, you'd see that certain tissues for certain organs develop in a certain area. It has some fancy names for that development, but tissues, though, when you look at them, can be, when you think about skin, if you say skin, everybody knows you're talking about a tissue. You say blood, people don't always think of that in their mind as a tissue, but blood is a type of tissue. Everything in the body is a type of tissue. Bone's a type of tissue. That's why it says hard bone, semi-solid fat. The difference is the characteristics of that tissue. That's how we separate it, because everything's a tissue, pretty much. So the 4 basic types that you can break it down into. 2 of them we're going to spend a little bit more time talking about during this lecture. Muscle and nervous is really going to be covered under block 2, but you have epithelial, connective tissue, muscle, and nervous. Those are our basic types. We're going to come back and define each one of them and how they're covering in line and how they generate forces. But when we look at tissues, though, they have to be connected. And so they do that by using intercellular junctions. We're going all the way back once again. We're going to actually use integral proteins, just like we use them to be potassium pumps. We're going to see that they actually help with connecting these cells. So intercellular junctions, if we just look at one slide, and then we'll define them, it's all these little junctions that are creating. Like in cardiology, I know you're probably already talking about gap junctions. How they allow ion flow to go fast from one cell to another because they don't jump outside of it. If you don't know what jump outside of it means, don't worry about it. We'll look at it in nervous. But it allows ion flow, it allows synchronous contraction when you look at the heart. Right? And what they're going to do, though, is yes, they're connecting these 2 cells, but they're also going to use proteins, cells that put into the wall, right? Back to our integral proteins, right? And they're going to connect to the microfilaments, intermediate filaments inside of each cell. They're going to anchor to that, those linker proteins. So the first one we see is tight junctions, and tight junctions are found anywhere you don't want things to get through. If you look at the bladder is an example where you would see tight junctions. Right? We do not want urine, and it's very bad if it does happen, leaking out into the abdominal cavity. Right? Very acidic for one thing, but you're going to get an infection. Blood-brain barrier. We don't want certain things making it to perfuse the brain, so there's a blood-brain barrier that's very selective. The way that it's going to do that is put a tight junction where you're going to have this space between the cells, and it's going to kind of look like a zipper. So these are membrane proteins, and they're just very close together, and it gives this kind of zipper-like appearance to where nothing can kind of sneak through here. Right? Sorry, I did it again. That same screen. It can't go between the cells. So when you get like into the kidney and other areas, you'll see that some things do what's called paracellular resorption, and it moves, instead of going through the cell, it goes between them. But a tight junction does not allow that, because then things would sneak by. That means that a tight junction, I know I'm talking way more than the simple slide says, but a tight junction then means the cell that's connected there, those cells have to be very selective. The blood-brain barrier is. It's only going to allow certain things in it. If they weren't tight junctions, everything would sneak by. Okay. Adherens junction. The definition of this one is we're going to see that there is a plaque on the inside of the cell. And this plaque, if you look at the lines in it, those are microfilaments. So adherens junctions attach to microfilaments and make this plaque inside of each cell. I mean, I'm hoping you can visualize, I'm sure you can. You know, this would be one cell, and this is the other cell. And then it's going to project some of those linker proteins, but we're going to name them, into the intercellular space here. And in this case, they're called cadherins. So you're going to have a cadherin there and a cadherin here, each one of these. And they're going to connect to each other in that intercellular space to help hold these cells together. So if you were just summarizing a slide like this for learning it, you'd say, well, adherens junctions form a plaque with the microfilaments in each cell and use cadherins to connect them between the cells. And cadherins are just transmembrane proteins, or initial proteins that go out. Desmosomes are similar, except for, I mean, almost in all ways is an adherens junction, except for they're going to attach to intermediate filaments. Drives me. It's funny, every semester I pick something that drives me nuts. I'm going to change my mind about what drives me nuts sometimes. That screen is going to drive me nuts. Alright, so it's going to connect to intermediate filaments, another part of the cytoskeleton, right? It's still going to use cadherins as the transmembrane protein. Similar, not exactly. Main difference, it uses it uses intermediate filaments instead of microfilaments. So probably a little stronger. Then you have a hemidesmosome. Hemidesmosomes are a half desmosome because you only have a plaque in one cell. Well, we only need that because we're studying tissues and we're about to look at this. If this was a cell, such as an epithelial cell, and it's starting at the basal layer of like your epithelia of your skin, those cells have to be anchored to something, right? So every cell has a basement or a base, and it connects to the basement membrane. Right? So what's going to anchor those cells to the basement membrane is what's called a hemidesmosome, to where you're going to have these the intermediate filaments there that are attached, and you still have the plaque. The difference is going to be here, is the protein that's used to connect those cells to the basement membrane is called integrins. So you're going to use integrins instead of cadherins. So, you know, I think this way to help me remember things all the time, and I'm like, okay, well then, since we're going to use a different protein to connect it, it's good, I like the name because it's called an integrin instead of a cadherin. So I think, well, hemidesmosomes help cells integrate into the basement membrane. Not really, you know, I say a lot of things that aren't technically true on that one, but it helps you to remember it. So, integrins.
I have a question.
Yes?
What makes the structure of intermediate filaments stronger than the microfilaments?
They're just larger, as in size. Like if you were to look at, did y'all hear that? What makes intermediate filaments stronger than microfilaments? And the only real thing would be their size. Because microfilaments are thin fibers that run along the inside of a cell membrane, just inside. If you picture Like sometimes they draw a square cell, so you can see it around. And then intermediate filaments are going all throughout. They're a little thicker, and then the microtubules are really big compared to those, the last part. They work out more. It's what I wanted to say initially, but I thought I'd be serious for a second. Yeah, they don't skip leg day. Gap junctions. Gap junctions have proteins. All of these have transmembrane proteins. What's going to make a connection between one cell and the next with a gap junction is what's called a connexin. And a connexin is just a channel. Okay? And so you're going to see that there's a channel that goes from one cell to the next. And I don't know how much they've talked about it yet in cardiology, but in order to move or to generate electrical potentials in the body, the current of the body is ions. Current in these lights is electrons, right? So we still have a current flow in the body. Current flow in the body is ion movement. And has he started talking about that yet? Okay, so you kind of understand. And you got the charges. So just like electrons have charges, well, so do ions, and if they're moving, we talked about it, right? We're going to really talk about it with neurons and see ion movement, how that causes action potentials, or how you touch your finger and your brain knows you touched something, how we send that message. But this way is very fast. Right? Not a lot of areas work this way. The heart's one of the big ones. It has connexons that are considered what we call a gap junction. So I'm going to define these out again, and then we're going to cover each type in detail. We have the 4 basic types. Epithelial tissues cover body surfaces. They form the glands, line hollow organs. Right? So our skin is an epithelial tissue. Serous membranes, a type of epithelial tissue. One of the larger tissue groups we have to discuss is connective tissues, because there are a lot of different types of connective tissues, from things that go under your epithelial tissues to blood, to bone, ligaments, tendons. All those are different types of connective tissue. And then muscular is going to be able to generate force and move bones, bodies around. It also can generate heat. And then nervous is what's going to do interacting with our environment internally and externally, and send signals or impulses either to the central nervous system to figure out what that is, or to cause a muscle to move or a gland to function. Okay, so we're going to start off covering all these different types of epithelial. If you look at an epithelium that's lining a surface, forming a protection, we're going to see that there is a free apical surface that would face the lumen or the outer surface. And then there is a basal surface, or the base at the bottom. And that's going to be attached to this basement membrane. Okay. Often with epithelial tissues, you'll see that there are secretions occurring there, such as hormones, mucus, a lot of times mucus, other substances. So if we looked at our cutaneous layer as an example, there's a basal layer that's anchored to the basement membrane, but this outer surface of the top cells would be the apical surface. But if you looked at one cell, because some cells are have one layer, and so if this was in the lungs, the small intestine, the basement membrane would be here, but this would be the lumen, right? The hollow part of your small intestine where the food's moving through. So the apical surface always faces that. Underlying them, you're going to have a basement membrane to help hold them. Right? So what actually happens is the basal surface down here of that cell is going to secrete what's called the basal lamina. We haven't quite got there yet, but down here is our underlying connective tissue. In the skin, we would say that is the When we get below the skin layers, we get subcutaneous layers. That's a type of connective tissue. We're going to get there, but that layer is actually called the reticular portion, and it secretes the reticular layer. And together, they're called the basement membrane. It's just how it's anchored down. Not as interesting as genetic disorders, huh? All right, functions of epithelial tissue. Protection, secretion, filtration, absorption, excretion. A lot of these we understand, right? I always mention this, I say it too much, I always study list, right? List, but I often think, well, do I need to study this list in my mind when I'm studying? Do I need to study this list, or could I figure it out? And then the second question is, okay, is the instructor that I'm looking at going to ask me to list them? Hey, here's 5 blanks, list them. A little tougher, right? Or is he going to say, here's 5 questions or 5 distractors, answer choices, and I just got to pick one? If that's the case, this list I don't need to study. Because is the skin a type of epithelial tissue? Yeah. I know I'm talking to some people always are like, come on, we all know this. Not everybody thinks this way. All right, well then flip it and say, well, if I ask you, you think your skin protects you? Yeah. You think it does filtration? Yeah. I mean, epithelial tissue as a whole do. You don't often think about filtration with your skin though, but it's there. Secretion, yes. Absorption, putting on that sunscreen that's apparently not good for you anymore. I don't know. I read another study that said only one. When you read one article, it doesn't mean anything. It says don't wear sunglasses. Okay, no. I don't know why. Excretion. So what I was saying is you kind of can reason that your skin does that. Your skin is not the only type of epithelial tissue. That's where we'll see filtration and stuff. Yes?
It might be dumb, but isn't secretion and excretion the same thing? What's the difference?
Depends on the type of tissue, and like a secretion would be from a gland, and it could be anywhere in the body. An excretion would be like just sweating. Okay. We're gonna get more into that. That's a very good question. There is a difference there. You'll see it as we go along. Just like in physiology, there's a difference between resorption and reabsorption. And the basis is, did the same cell that put that out there resorb it, or did it do reabsorption? Or it reabsorbed it, because it put it out to begin with. But if another cell picked up something one cell put out, that's resorption. It took it in, but it didn't put it out there. I'm saying that's another example of how these medical words could be confusing. I think he goes into that in A&P I, I don't know. That's actually a good question. Okay. Epithelia. We gotta name them. This is gonna help you. As boring, I need to quit saying that some things are boring because it winds up on my critique. People go, he does a great job with some boring stuff. I hear exactly what I said back to me sometimes when I was a kid. It's not boring. It's just a little more monotonous. You know, I like anatomy, but when I look at this versus when y'all look at it for the first time and you're trying to learn it, you're like, my goodness, what is the use of this? And that's why I like to say, well, why do we need to know this? Right. I know this, though. When you're studying radiology reports, or you're studying lab results, or even more important to y'all, you're taking a dermatology test or something here at IPATH, or you're taking the PANS. One of the things that will greatly help you, and you will see you use yourself in clinic if you actually take the time to read some lab reports, right? Because we don't always do that as much as we used to. You don't have to, they decipher everything for you nowadays. Even radiology reports always come with a lab read, wet read or the actual read, and people wait for that, and you get busy, but I always like to read it. Sometimes I used to go down there, that's why I like inpatient medicine. Just do it myself. Because I'll remind you of this. Everybody trusts radiology so much in a hospital. But in every field, everywhere you've been, there are people that are just not good at the job. I mean, may hold 4 or 5 degrees, but they just, and everybody has off days. So if it's a really important read, you know, I say as even as a PA, you know, we're not radiology experts, a lot of us, but read it, see if it makes sense, you know, with what your patient presented with. Or did they just comment on stuff that had nothing to do with what you wanted them to look at? Or did they miss the fact that, you know, there's, you know, I see providers all the time go back to radiology and go, hey, you've noted on this, what's that in the pancreas? You know, they might have had an cyst or something in the pancreas that needs to be addressed, but they never addressed it on the initial radiology report. That's a long spill to talk about epithelial tissues, but that's good info. You know, treat your patient like they're part of your family, you'll be all right. Okay, so I wouldn't want to miss out on my thing. But the layers, why it's important is when I read something like that, if you tell me they see a like columnar tissue in a certain area, and I know that columnar tissues are found generally in certain areas, that's what I would expect if that's where like that biopsy's from. But what if you're biopsying an area that has simple squamous, not cuboidal, and they say, hey, there's cuboidal tissue here, I'm making a generalized example. Well, that's a problem. Why did the tissue go through metaplasia? Why does it change? There's a disorder there. So knowing the tissue types can tell you what you're looking at, right? Or whether there's a problem. You'll see that as you go along. But for now, we're just going to learn how to name them. And we'll learn the basic areas we find them. So you can have different layers, and we're going to see you have simple, stratified, pseudo-stratified. We're going to go through each one. So the first way we can name them is using their shape. So if you look at a cell, and it's kind of flat, and it looks like a paving stone that you might walk on, right? That's called squamous. If the cells look like a die, or a set of dice here, where they're as tall as they are wide, that's called cuboidal. And if they're taller than they are wide, they're called columnar. So that's one way. We're going to combine the ways to name a tissue. So you can have squamous, cuboidal, columnar, and then we can take it to the next level and say, okay, well, we can also name them by their arrangement. If there is one layer of cells and they're all in contact with the basement membrane, it's called simple. One layer of cells on a basement membrane is a simple. If you look at, I'm going to jump over and say, well, what about stratified? Stratified means that there are at least two or more layers, right? But the only layer that's in contact with the basement membrane is the basal layer. So in this situation, only the cells down here are in contact with the basement membrane. The rest of these above it are not. And they get all jumbled up, so they call that stratified. Your epithelial tissues are stratified, right? Not all of them are in contact with the basement membrane. Pseudostratified is a variation of that. So pseudostratified appear to be stratified. They appear that not all cells go to the basement membrane. Right? But in fact, if you were to pull these apart and dig through them, or you're looking through somebody's hair, I was thinking, you would see that every one of these cells does contact the basement membrane, but not all of them, like if you look here, not all of them go to the apical surface. And then you think about it, and you say, okay, well then that means that all those are columnar cells, as we look at them, they're all in contact with the basement membrane, and the definition of a layer where they're all in contact with the basement membrane is simple, right? But you have to think, right? Why would you not, if you were the one naming all these when you originally saw them, why would you not want to name those simple? Because then it doesn't tell you, like they came from a certain area. And so when they looked at them under a microscope, they just obviously looked and said, oh, they do all contact, they don't all go to the surface. So you need a name for that, so they called it sort of stratified. It appears stratified, but it's not. So they came up with a fancy word, pseudo-stratified. All right. Like I pseudo know about genetics. Pseudo. Genetics is so interesting. Of course, I like to watch forensic shows and stuff. I don't know about y'all. You're gonna love it. Okay, the next one. So we're gonna take these, naming criteria, and then we're gonna add them together, and we're gonna say, okay, well, what about if you said it's a simple squamous epithelium? That means it's one layer, they're flat cells that look like paving stones, and so they call it simple squamous. You have one layer of squamous cells, and in this case, you're gonna find them like in your lungs, the blood vessels. I actually have I didn't list where we find them on every slide, because I want you to pay attention to, at the end of these tissues, I'm gonna show you a picture of a person, and it lists the basic areas you might find a certain type, and that's the part I kind of want you to know when you're looking for where they're at. But it's important with these because in the kidneys, the lungs, the serous membranes, they're all a simple squamous. And that allows, most people understand the lungs exchange oxygen and carbon monoxide. And so you have to have cell layers there. But if you had more than one cell layer, the exchange of CO2 and oxygen would not only be slower, it just wouldn't happen as easily. You'd have to go through or between multiple cells. So a simple layer allows rapid exchange of things. So that's the areas you might find it. Blood vessels, heart, kidney, lungs. Simple cuboidal means you have one layer of cuboidal cells. You see these also in the kidneys and lining some of the other glands. But a lot of times we say simple cuboidal, we're looking at like kidneys. When you look at simple columnar, one of the things you're going to find is there are variations of simple columnar cells. So you have one layer of columnar cells, and they, depending on the area, will have microvilli, sometimes on their apical surface. Other times they'll have cilia. Cilia is just a longer microvilli, it's just a little longer. You'll have these yellow-looking cells here. These are called goblet cells. Whenever you see columnar cells, some of them will change into goblet cells. So almost all the time when you see a simple columnar layer, you're going to see goblet cells there. And anytime you hear the word goblet cells, just think mucus. They secrete mucus. And I didn't put it on here just yet, but where we're going to see a lot of these is in the intestines, right? Where we need a lot of mucus, right? So it's going to come back and we'll see what it's used for. Another way is to say, well, pseudo-stratified columnar epithelium. It sounds like a big word, but now that we went through them, it's really not. It's one layer of cells that look kind of stratified, but they call it pseudo-stratified. They're columnar, they're a type of epithelia. Once again, they just don't all go to the apical membrane, but yeah. Because they're columnar, though, you're still going to see goblet cells, microvilli. Sure. Yeah. We still got quite a few of these. Not quite a few, just a few. So if we go back and say, well, here's stratified squamous epithelium. I'm using this to show you something, because we're going to go into layers that have more layers than just simple. Anytime you look at a picture, if you were to look at this picture, right, and you said, okay, what type of cell is this? If you're basing it on its shape. And let's look and say, well, what do these look like down here at the basal layer? Yeah, they look, you got the point, they look cuboidal. Alright, so what's up here? Squamous. So when you name a tissue, it is named for the way the tissues look at the apical surface. So in this case, that is a stratified squamous. It's stratified because there's more than one layer. And this is actually a picture that we would see of epithelial tissues. when we study the integumentary system, we're going to see, sorry, that the cells at the basement membrane are multiplying, and as they move up and start to die off, they flatten out, and they become squamous. So you would name them stratified squamous though. And as they die off, which we'll get a lot more into in integumentary, you're going to start to become keratinized. And so different layers of epithelial tissues of your cutaneous layers here will either be keratinized or non-keratinized. If it's non-keratinized, all that means is the nucleus is still alive and the cell is not full of keratin yet. You don't need to understand that for this test just yet. You just need to be able to name a tissue. Right? For this test, it doesn't matter whether it's keratinized or non-keratinized. But I just like to mention, if you look inside it, there's no nucleus. Right? These are dead cells, just like when you rub your arm. Those are dead cells. They're not only dead, they're full of keratin. And don't write this down or anything. Don't listen to it if you're reading the recording later. Is as the cells progress up and they die off because they become there's intermediate filaments inside of those cells that become keratin. They're called tonofilaments actually now. We'll get to that. That's why I said don't write this down. And it becomes keratin, and as keratin fills that cell, the nucleus dies. Right? And so when we look at different types of stratified squamous tissues in our skin, they would be keratinized. But there are areas of the body where you have stratified squamous tissues that aren't, they're not dead at the apical surface.
Is that the same as callus?
A callus is the skin's response to like rubbing and stuff. But a callus is going to generally be keratinized. So those cell layers are dead out there. But they're abnormal because of the way they're growing, because of the friction you're putting on them. So then you go, well, wait, you talk about epithelial. No, I'm sorry. That's all for block 2. Let's get out of that. We're just naming them. I just want you to name them for now. I don't want to get off into down the road stuff. Okay. Stratified cuboidal epithelium. That means if you hear the word stratified, we already know that there's more than one layer. And then there's only one layer in contact with the basement membrane, but there's more than one layer of cells. So you have 2 at least or more. We find these in like esophageal glands, sweat glands, and when you look at them, you're going to see that you have that basement membrane cells, and then cells that are not attached to the basement membrane, and they look like a dye, so they're called cuboidal. And then the last one here that we talk about is transitional. You're going to find transitional epithelial cells in areas like the bladder. So when the bladder is, full, the cells will look flat. But when the bladder is empty, they look more kind of cuboidal. So they call them transitional because they notice them at different stages. They look different, but that kind of makes sense, right? The bladder can only fill so much, and it starts filling, it's going to flatten the cells out in its cell wall. When you go to look at pictures of these, it's hard. It's hard to ask somebody, is this cuboidal? Or is this cuboidal? Transitional and cuboidal cells look very similar. And in books, they don't depict it great. But actually, if you looked at a relaxed transitional epithelium, you would see that the apical surface is more domed than when you look at the cuboidal. It would still be a little bit domed. They got specific. So what I was trying to reference is it doesn't make a good question to go, to point at a cuboidal looking cell and say, is that a transitional or, because they all look the same to me. They all look domed. So, but it's just knowing the definition of where you find these, and that's where this comes in. So this is where I want you to pay attention to, like, where you find them, right? So stratified squamous, we often think about it as our outer layers of skin. When you look at simple squamous, they make up epithelial membranes that line blood vessels. Now one of the things you'll see when you look at it and say, well, stratified squamous, forget about keratinitis and all that, but no, don't forget about that. If you have a stratified squamous tissue in an area that's not keratinitis like your skin, they're still alive, that tissue is still tougher. So areas in the body that go through a little more friction or abrasion, like even inside, you would have that stratified squamous. It would be keratinized, it wouldn't be dead. When you see simple squamous, right, that's those softer areas a little bit. And then columnar is going to be your digestive tract. That's why there's so many goblet cells and mucus. And then you have pseudostratified columnar. In this case, they put ciliated. So if you have a pseudostratified ciliated columnar, that is actually specific for looking at areas like the upper respiratory tract. Right. So it's still columnar, but they've now specified more, so you know where it's coming from. When you look at transitional epithelium, it says bladder, and then cuboidal lining, the ducts of sweat glands, things like that. So pay attention and make sure you know where you generally find it. It'll help you now, it'll help you later. So we're not done with the epithelial tissues yet, because they're covering and lining. And when you look at blood vessels, when you look at serous membrane, so the whole circulatory system, the inner layer, is a type of epithelial tissue. But to designate where it's at, they called it endothelium. So endothelium is no different than other epithelial layers. It's just now we're saying, okay, well, there's epithelial tissues, but if you say endothelium, which is the same thing with a different name, because it says, well, now we're talking about the circulatory system, blood vessels. But if you say mesothelium, you're talking about serous membranes. Serous membranes are also an epithelial tissue. The pericardium, the pleura, the peritoneum, those areas where we talked about, you have visceral and parietal layers. And there's serous membranes. Well, they're the tissues that make up those serous membranes are epithelial tissues. Y'all see the link there? It's not the same thing, it's just you're talking about the same area. Alright, and then glands. So glands are part of epithelial tissues. A gland can be a single cell or it can be a group of cells. Right? They can be unicellular or multicellular. If you look at a gland, it's going to say, well, here is, is it exocrine, endocrine? Does it use a duct? Right? Where is it going to? A duct, the surface, or directly in the blood? So we're going to break down and say, well, what's an exocrine and what's an endocrine gland? Exocrine means we're going to secrete to a surface or a lumen. If we look at their cellular level, most of these exocrine glands, and just think of exocrine glands as going to the outside of the body or into an area that does open to the outside of the body, a lumen. Right? So if you look at the intestines, you don't often think about it that way, but there's an opening at each end, right? You got your mouth, you got your anus, they're open, and so that's a lumen that goes all the way through. And so if you have a gland that's secreting into that area, that's an exocrine gland. Right? When you look at endocrine glands, they generally release or secrete into the extracellular space. They don't have ducts like exocrine glands do. So they're going to diffuse into the bloodstream, in other words, hormones. So technically when you look at a hormone, if I asked anybody in this room before I even started this, I said, well, where does a hormone release its product? Everybody, and you're fine saying that, you say, well, into the blood. Because hormones get released into the blood and then they circulate throughout the body. Right? Exocrine doesn't do that, endocrine does. So if you release a hormone, not that you have to understand this, but what really happens is that cell, you know, when you look at a endocrine system cell, it's gonna release it into the extracellular space, or like into the interstitial fluid, and then it's gonna diffuse into the blood. That's like a pure anatomist, like my old boss always say. He would make me leave. He'd always say, he'd come in because he'd like to see slides sometimes, and he'd go. He came to me after one day, and I had endocrine glands lost their ducts, diffuse into bloodstream. And I said, the hormones, it was what we all understand. And he is a pure anatomist or PhD anatomist. No. Hormones do not get released into blood. You know what I mean? And I'm like, okay. I didn't roll my eyes like I just did to y'all. Because I respected him a lot. I respect y'all too. You know what I mean? It's funny, I'm catching myself 2 days in a row. I catch myself when I say something, but sometimes I don't catch it. If I don't catch it and you don't ask me, you're the only one that's going to be irritated for life. If I say something and you're like, I'm one of those people, you got to walk up to me and go, hey, I don't mean, what did you mean by this when you said that to me? And I'll tell you, the most time it's probably not what you think I meant. Because I make those mistakes, but respect y'all too. Anyway, he wanted me to say, no, it's got to go into the extracellular space first. I'm like, okay. So it's there still. He's gone. But I miss him. I wish he was back. He was a tough instructor. So his version, like when we teach, he taught neuro a lot. When I was here in PA school, he taught neuro. And he would come in, and he still did this. He would teach this whole A&P1 class. But he taught it before I came back to it. This one. Very, very smart guy. Sometimes people are smarter than us teach at a different level than we do. He had done it for so long. When, like this lecture, if he had came in, what you would have gotten were about 30 slides with pictures. Do you remember Dr. Kemper? He would just bring in 30 pictures and talk for 2 hours on them. Of all the same things that are on my slide. He wouldn't miss talking about that, but he would expect you to just be in this dialogue with him the whole time. It was tough.
He liked his whiskey, right?
Probably.
And he always had it feel like a bottle at his podium all the time, showed off.
How do you know that? One of my instructors, that's weird, because that's a long time ago. One of the instructors when I was here taught, I don't know what he taught, maybe geriatrics, but he had his own cough syrup. And then he was talking about it. A bottle of cough syrup, but he made it at his house. And if you don't know how to make old school cough syrup, go look it up. Better than NyQuil. But, no, Kemper, I don't think Kemper drank on the podium. Okay. He'd be happy we're talking about it. A little bit of a digression of it. Let's look at exocrine and we'll take a break. Under exocrine, multicellular, they're going to have functions, where they're secreting things. There are different ways that we release these products. There's American, and yes, I'm from East Texas, and that's hard for me to say for some reason. American. I sound like I'm in a Western movie every time I say it. American. Merocrine, apocrine, holocrine. I changed the name a little bit when I say them because American is the most common way that exocrine glands will release their secretions. Right? What's going to happen in American secretion is you're going to have exocytosis. So in that case, the gland's not damaged at all. Actually, this happens over and over. It's happening in you every second of the day because if you look at neurotransmitters that we use in the body, they're released through American secretions. They would be released the same way in that they're not a gland releasing that, but they release their products out of the cell by exocytosis into the space or wherever it's going. So nothing happens to the cell. If you say apocrine glands, and I often put an extra, y'all have to tell me in the hallways and stuff if when I do this stuff it helps you or not, because I believe it does in my mind 100%, because I may have 68 people in here, 67 going, why does he do that? That doesn't make any sense to his thinking. But I put an extra P in here. Look. I call them apocrine glands. Why? Because the end of the cell breaks off during this secretion. The cell still remains alive, but they produce these membrane-bound vesicles by decapitating itself. They pinch off a portion of the head. They pop the head off. I call them apocrine glands. That's how they release their secretions. And the last one is looking at Hollican glands. And I once again do a little wordplay here, and I put a W out here. I would have done this if I was there when they made these up. But I wasn't there. Why did I put the hole? Why do I want a W there? Hollican. When Hollican glands release their product, the whole cell ruptures. So it's gone. So a sebaceous gland is a Hollican gland. When you talk about sebaceous glands, those are oil glands, like in your face. And anyone who's dealt with, well, everybody, but if your face, you got a lot of oil glands and sebaceous glands, they release this product. The cell actually dies, and it ruptures. And so you're going to have cellular components inside of that area where that sebum was too. That's why we get acne, different things, one of the reasons. But that's the way they're released. So the dead cells are moving up, and they're rapidly replaced by mitosis. They don't make more cells as they do this. So American, most of the glands in the body are American. They release by exocytosis. Nothing happens to the cell. African glands, apocrine glands, they release by breaking off or pinching off, or what they call budding off, part of the membrane. And then Hollican glands, the whole cell dies. All right, let's take a break, and then we'll do the rest of it. I love these first 2 weeks. All y'all are so hard. I feel like paying attention. They are taking notes. They calm down their study stuff. And they look at what I'm interrogation and talking about I've been 3 years. My first
I go to bed a little earlier if I can.
I was in bed at 11 and I'm at 4:40.
It's easier to sing the
No, like when they order it,
Oh, yeah.
I think it's like a branch of, it's like a job, Starbucks product. Sometimes I do that. Not this
I control the switcher in my house. Oh, you're controlling
There's a little one. So I'm just gonna play with it till it turns on.
You have a boil that go downstairs. Yeah. I have a question. And all for like you. I like to like you the chip for curing.
Put it underneath, you know, that little.
Oh, that's what I'll do it.
Dude, it's so long weekend. I saw it. You want flat first? I used to especially when you're inside.
The only comments that A&P I like better than the double. Yeah, I should. That's just like one of those.
There's a problem with it's called but it's like you're trying to list it's worse than stuff. Yeah, I just had to. The one time we went, I was like, I'll try it, and like I was just looking at like the ones. There's a Reese's mocha, and like actually has Reese's on the top. Well, it's because they just like put like the syrup, where the cold one, when they blend it, they put whipped cream and then they put the Reese's on top. And I'm like, yeah.
I don't think it's
Yeah, it's literally,
yeah.
like I didn't taste any coffee.
It doesn't really taste like it. You go to Cole's I'll bring it tomorrow. Like, just so you can
She said that one to you, and she also
because my mother-in-law got like this whole like set and he food. I tried it on my
I'll be in my head. These, it's just you turn it all like one like you don't put it out on my I turn it all in and then you just choose like a little that's actually perfect. Yeah, the AC.
They want to ruin my computer. Sorry, I'm the computer. So last week, somebody was talking about how bad their computer was. I'm like, man, this new one they gave me is perfect. And like the next day, I got an email that said, hey, you need to take your computer down. We're going to do migrate it again. And I just got it. It works perfect. So they're obviously going to mess it up. I don't like taking my computer down. Their computer, I said mine. They can have it. Sorry, man. Okay. 4 basic types of tissue. Well, now we're going to transition and talk about connective tissues. We see connective tissues everywhere. Sorry. Because when we look at things like bone and cartilage throughout the body, that's a type of connective tissue. When you look at your internal organs and you have fatty layers, different things around them that protects them, connective tissues. Fascia that we see surrounding muscle and muscle compartments is a type of connective tissue. Now, I mean, I can go through this list. Blood, fat, adipose tissue is fat tissues where they store fats. And immune responses. So microbiology, you are talking about the connective tissue, like a white blood cell is part of the connective tissue. So you could just say, okay, well, there's nervous and muscle tissues, yeah, and there's some skin cells, epithelial. Then the rest of it in the body is connective tissue. There's a difference when you look at it. If you look at epithelial tissues, you're going to have a lot of cells. When you look at connective tissues, you're not going to have as many cells. Right? What you're going to have a lot of, though, is the extracellular matrix. Right? It has nothing to do with Keanu Reeves, but it's the extracellular matrix. This area that's inside, or around the cell, something not inside, around the cells, or inside the connective tissue. So when you look at connective tissues, you'd say, yes, there are, like the bullets are doing, there are cells, and then there's an extracellular matrix. Once again, think of the extracellular matrix kind of like a Jell-O mold. Then you're going to have a bunch of stuff that's in that Jell-O mold, depending on who made it. Right? So the Jell-O part of the Jell-O mold, what you look at is the ground substance. It's part of the extracellular matrix. And then you'll also have different and varying types and amounts of protein fibers. So break it down that way. When you say extracellular matrix, what you're talking about is the protein fibers and the ground substance. And there are different types of ground substance. Right? We're not going to look exclusively at all of them. Normally it's combinations of what they call polysaccharides and proteins that make up this whole area. And it's going to come from the connective tissue cells themselves. They're going to secrete that out into that. And it greatly is going to determine the quality. Like, what's the difference between bone and like a tendon? Well, it's going to be the quality of the ground substance that, we'll get into that. Okay. So one of the key things is as you're developing embryo, you have a certain type of connective tissue to start with. So mesenchyme is the original connective tissue. There are many ways to say this, and so that you hear it different ways. You could say, like, all connective tissues are derived from mesenchyme. Or you could say, and using another word, you could say, all connective tissues arise from mesenchyme. No matter how you say that, all it means is that mesenchyme was the start. So any cell that we talk about that is considered a connective, any tissue that we talk about that's considered a connective tissue or a cell, connective tissue cell, ultimately started as mesenchyme. It is the precursor to all connective tissues. I said it 3 or 4 different ways. Those are saying the same thing. Okay. So the progression of cell type stuff. If you haven't studied like cellular anatomy a lot and look, you got to pay attention to endings. Because if the cell has blast after it, right, that's an immature cell. So blasts are derived from mesenchyme. It's the cellular progression. So you have a mesenchymal cell, and then a lot of times you'll have a blast cell. It's an immature cell, a bud or a sprout. Or the, like I in my life have a 23-year-old Jacob Blast. He's still an immature Jacob, so he has a blast after his name. He doesn't get it when I say that to him, because I don't explain it to him. But he will grow out of that. How do we know that our kids will probably grow out of the craziness? Anybody got kids that are younger? My youngest now is 17, so under that? Who has kids like 3, 4? Yeah. All right, let me tell you something. It doesn't get better. It gets worse. Enjoy those moments. Because everything you think is driving you crazy now, you're going to look, oh man, I wish I could go back there. I'm being dead serious. Especially once they start driving and you want them to, I don't know, I'm off on a digression, I shouldn't do that. But you want them to be able to support themselves and be on their own as an adult, right? Well, if your kids, I've decided this with my kids, and I tell my wife this all the time, and she gets mad at them, because it's harder, because they can go out and drive, they can get in a lot more trouble, they can do stupid decisions that they're going to do, and you no longer have the control that you had when they were 3 or 4, and they're driving you crazy because they're going in and out of the door, or whatever it might be. That's nothing. So, they hear people say, yeah, oh, it gets better. No, it doesn't get better. But you'll enjoy it anyway. Enjoy Little League. Parents are great. But when they get to be an adult and they get out there, all the things that my kids do that irritate my wife, I'm constantly reminding her, we want them to do that. She's like, they don't tell me this, they don't tell me this. I just went and scheduled her follow-up doctor appointment, didn't even ask me about it. I'm like, that's what we want. You want a kid that when they're 18 to take care of themselves, right? I'll finish it out with a negative statement. I did not go with, I've had 3 kids go to college, and I didn't go to college with them the first day. No. I moved stuff in one day, but in that big drop-off day, the first day, no, they're adults. They can do it themselves. I don't handle their bills. I pay them, they pay the school. I have a house in College Station my daughter stays in. She's responsible for making sure the bills get paid. That's the way in other words, I was going to finish with this negative statement. Do not drive 3 hours from Bernie, Texas to College Station every week to do your kids' laundry. I don't, all y'all in this room like, I would never do that. There's somebody in here that would do that. They'd be wearing dirty clothes. Okay, sorry. See, I didn't make it through the day without doing one of those. It's hard for me. Let's get back. Sorry, let's connect the tissues. I'm going to stop. I'm going to stop there. The problem is in the hallway, they keep coming. Keep doing it. So Jacob's a blast. He's immature. Mature cells are then are differentiated cells. So, like you have an osteoblast, is an immature bone cell, but it also is what helps to make new bone, right? Or remodel bone. But mature cells end in cyte, C-Y-T-E. So if you have an osteocyte, it's generally derived from a blast. So the cellular progression would have been mesenchymal cell, blast cell, cyte. Right? We're always going to look at cellular, what they call lineage, where they came from. Right? So blast cells generally are going to be mitotically competent. Just means that they have the ability to go through mitosis. I didn't say it this way yesterday, and I thought of this too. I was going, if you just generalize mitosis and meiosis, you would say this. Mitosis, the reason for mitosis is to make new somatic cells. The reason for meiosis is to make gametes. That's a simplified way of defining those two. we talked about how we do all that, but that's the underlying. So blast cells are mitochondrially competent, meaning they can go through making new cells constantly, right? Once cells mature, they generally don't have the ability to go through mitosis anymore. But they do help, right, maintain what they call the matrix, an extracellular matrix. They can help maintain the qualities of that once they, so if you take a chondroblast, which becomes a chondrocyte, so you have an immature cartilage cell called a chondroblast, it will become a chondrocyte. Osteoblast will become osteocytes, immature. Another characteristic of connective tissue is not all of them are located and stay in one spot. They're either fixed or mobile. Right? So we're going back to micro, Holzberg's micro there, of white blood cells. White blood cells come in different forms. There are a lot of different names for white blood cells. Right? But in general, white blood cells can move to an area in response to infection, inflammation. In other words, the inflammatory response, they can actually move throughout the body. They can move throughout connective tissues depending upon the quality of it. Right? So some connective tissues move about, and when that happens, or some other, sorry, we're switching gears up. Some other connective tissue cells can kind of move about within the connective tissue itself, like a fibroblast. The fibroblast secretes fibers. These are protein fibers, or that make up the characteristic of that tissue, but it's going to secrete the fibers in the connective tissue and also ground substance. When you look at wandering macrophages, right? Macrophages, like we said, are derived from white blood cells. Macrophages, there are a lot of different names for them based on whether they're mobile or they're fixed. But in general, they can wander around and go to sites of infection. When you look at connective tissue cells that are immobile or fixed in place, you're going to find those in areas like the spleen, the lungs. We'll name them in a second. So some are fixed, some are mobile. You have osteocytes, chondrocytes, great. We'll get back to that in just a second, but here's the most common cell of connective tissues. Well, connective tissue's quality is dependent upon the extracellular matrix and also the fibers. There are different types of fibers, right? There's strong fibers, a little bit weaker fibers, then there's elastic fibers we're going to talk about. But fibroblasts secrete these. Right? Fibroblasts is the most common connective tissue cell. And we see fibroblasts, and you do not, these caricature-looking book pictures, you do not need to label these for these tissue types. I'll say it each time, but you don't have to label this picture. It's not going to be a study picture again to you. It's just an example to kind of show you that there are these green-looking, they're not really green, but fibroblasts. And they are secreting all of these different fibers depending on the connective tissue type. So they migrate through the extracellular matrix and maintain the matrix and secrete the fibers for that tissue. That's why they're called fibroblasts. Macrophages develop from monocytes. That's, once again, hard part of anatomy, right? You just said white blood cells. Well, white blood cells are what? It's all lineage, right? Monocytes, white blood cells, they're irregular shaped, and they often have photophilia, philopodia, sorry, I said that backwards, that can go out and engulf a bacteria, right? It's going to come out here. It's going to help move it, and then it will engulf the bacteria. Remember, it's going to engage in phagocytosis, which is a form of endocytosis. The philopodia is going to help move it. Actin is a contractile protein that helps to move things in some cells. Right, so we said macrophages then can be fixed or they can wander around. I said it several times, but it's just making the difference when Micro talks about them. So if it's a wandering macrophage, by definition it can wander to sites of infection because they don't hang out in great numbers in some tissues, but then they rush there. fixed macrophages are always there. Okay. We're going to leave it kind of at this. Macrophages have many different names. So when you look at a Kupffer cell, that's a macrophage in the liver. Right? Once again, they named them to show where they're at and whether they're fixed or mobile. I don't care that you can define out every single one that's fixed or mobile, but I do want you to know if it's in a certain tissue, like a Langerhans cell is a macrophage found within the cutaneous layers of the skin. Osteoclasts are a type of macrophage found in bone. So now we have 3 bone cells we've talked about. We have mesenchyme, we have osteoblast, and we have osteocytes. Osteoblast, or so I'm going to say it this way, osteocytes are derived from osteoblast. They were blast first, and they became an osteocyte. Osteoclasts are not in the same cell lineage, because osteoclasts are a monocyte, a macrophage. White blood cells. They come from the white blood cell line. But an osteoclast breaks down bone. So think about macrophages and what they do. They kind of break down things. Yeah. So osteoclasts are going to digest bone, basically. Alveolar macrophage, talking about dust cells that are found in the lungs. Monocytes, just in general in blood, are macrophages. And then microglia are found in the central nervous system. Within the CSF, that kind of stuff, there's microglia that help clean up that area. They're a type of macrophage. All right, we're moving on to plasma. So plasma cells are formed from B lymphocytes, and they're important because they're what secrete antibodies. Alright, so let's link that and say, well, where do we generally think we'd find them? Well, you're going to find them in areas generally that are open to the exterior in large numbers. Because the GI tract, the respiratory tract, both open to the outside, we're constantly exposed to different bugs, viruses, bacteria, that kind of thing. And so we need to develop antibodies to those. So we want that, this is my mind talking through, not the book. So we want that, if there's something that's going to get into my body and hurt me, and my body, in order to fight it, needs to make antibodies, I want that to start as soon as possible. So like in your mouth, you're going to have higher levels of these plasma cells that can secrete antibodies and start telling the body, triggering the immune system. But if you have an infected tissue, you're going to see a lot of plasma cells there also. They're going to accumulate there. Okay, so that's plasma. Mast cells you find is another connective tissue cell type, and they sometimes can be phagocytic like a macrophage, but most of the time we study them for what they're storing and using inside of them. Because I don't think Micro started talking about the inflammatory response just yet, but they're going to, and you're going to see that mast cells are involved. A lot of things are involved, but mast cells store things inside of them, and they can also make things. They're called mediators. So if you have a mast cell, I'm giving you a little bit of Micro, but not enough, just enough for you to be dangerous, I think. If you have a mast cell sitting there just in a normal, nothing's going on, there's no infections. They store inside of them things like heparin, histamines, proteases, and oral sulfatases. If you don't know what those are, that's fine. ECF, I put a box on there just that people would always ask. You don't need to know it in here, but it's acetylchemocactactor. Here's the point for me is I want you to understand that mast cells store primary mediators. Actually, I'll go further, and you can write on there. I don't even care if you learn the list of what they're actually storing. I want you to understand that mast cells store primary mediators, so they're ready to be used if an inflammatory response happens. And then I'll let Micro, because I'll let them spell out the details for you. They also have the ability to make things that need to be, right? Because we understand, a lot of these we understand. Histamines are part of the inflammatory response. Heparin, you may not understand, is involved, you gotta clot things off, different things. And you're gonna understand this a lot more when they go through that. Secondary mediators are just made on the spot, when they're needed. So they store primary mediators, they make other things on the spot, like prostaglandins, cytokines. You remember COVID? What was a big initial thing with COVID? Cytokine response storm. Right, this is where it came from. Which just reminded me that I was what they call patient zero in this building that shut it down. The day after I left here, they went to online learning for the next year and a half. You want the story now? It is a story. I went to Colorado and went skiing. And I was reading a report as I was traveling back from skiing over spring break. And they said, hey, if you went to Colorado skiing, the health department in Colorado said you probably ought to, you need to be a little concerned because we have this outbreak of COVID starting or something. I'm like, okay. So me being kind of by the book a lot of times, I know it doesn't always seem like it, but I texted or emailed my boss and said, Sunday, I said, listen, I got to teach this week. This thing came out in Colorado, but I'm planning to be to work because I don't want to get into who likes COVID, who doesn't. At the time, I said I could care less about it, and I still do. And I said, but just to be on the safe side, because I have this knowledge that the health department there said you probably should not go around people, and I feel fine. I said, you want me to come to work or not? So he ran that all the way up to like 2 colonels. Around here, you got colonels that work, colonels, that kind of stuff. It's weird. And so I got all this traffic back that said, yeah, you can come to work. So I came to work on that Monday or so, I don't know what day it was, and I went home that night. And I woke up in the morning and I felt like I had the flu, like I had chills, it was just so different. But I'm a person who, I'm gonna work all the time. I don't like to stay home. And so I'm driving out of my property and I get about a mile down the road, and I'm still not on the main road nowhere. What the hell am I doing? I'm a civilian. I don't feel good. And that's when you know you're probably a little sicker for someone who goes to work. And so I texted my boss, I said, listen, I ain't coming in, and they're talking about that stuff, in the beginning. I said, I'm just not gonna come in. So I didn't come in, and I called the clinic over at Camp Lewis, said, I wanna come over there. I ain't feeling well. So they said, oh, you gotta be tested for COVID, and that's when it all blew up. And so I went, and they came out of Camp Lewis Clinic in a hazmat suit. They wouldn't even let me come in the building. They came out in a hazmat suit and did the tests and stuff. And they didn't even know what they were doing at the time. It wasn't even like a regular COVID. Anyway, 2 days later, because it took like a couple of days, and they said, hey, you got COVID. I'm like, okay, great. Anyway, as soon as I told them that, and they fumed, there was probably still haze on my computers and stuff in my office. Because they came in, and I don't know what they did while I was gone, but there was a haze all over the room. They were, where all did you go in the building? Who did you contact? I'm like, what do we do normally on Monday mornings? Take a test. I said, all right. They said, so you gave a test, so you weren't exposed to a lot of people? I'm like, no, they raised their hand, and I go to every single one of them. They're like, which bathroom did you use? Which this? I'm like, I said, luckily for you, I walked straight out of the building after class and went home. That first day when I didn't feel sick. Anyway, that was it. After that, they came and shut it down and fumigated it, and it didn't change anything. Sorry, I didn't mean to make that story so long, but I was patient zero here and in Kendall County. It made the paper. And I thought that, man, I never seen people be so ugly. Like talking about, find them, string them up, tar and feather them. Y'all remember those days? I'm like telling my kids, hey, no, we don't talk about this. We've never talked about it, except in here. Because now, whatever. Okay, those were funny times. I'm glad to have lived through it. I got to spend 2 weeks in my RV on my property, and I could go out on my 93 acres and walk all morning. But they weren't supposed to be around family, and that was bliss. So you want me to live in my RV for 2 weeks? Yeah, You got it. You got it. They're bringing me prepared food out and stuff. Awesome. Go back. All right. For people who don't like the digressions, back to types of connective tissue cells. Adipose cells are cells that have the ability to store fats. But they can synthesize and store lipids, but most of what they do is store fats like that you eat. One interesting fact that's not on here about adipose cells is that you can make new adipose cells. You can make new fat cells, but you're not getting rid of them. When you lose the fat that's in those cells, the cells remain ready to store again. If you decide, if you want to diet, lose a bunch of weight, you lose fat, but you don't lose fat cells. And so if you continue to put on weight, fat, you'll just make more cells and continually fill them. That's kind of, unless you do liposuction or something, you'll suck all those out of it. Just remember, some people do die from that. From everything. Leukocytes. Leukocytes are white blood cells. Read the second statement, not found in substantial numbers in normal connective tissue. When I read that at first, I would go, well, why are we talking about them? We're talking about connective tissue cell type. That's not what that means. What that means is if you don't have an infection or an inflammation, in other words, you don't find a lot of leukocytes or white blood cells in an area unless it's going through the inflammatory response to an infection or something. In other words, they're going to move there. And so when we look at labs for tissues or blood, let's look at blood. You do a blood sample and you want to take that lab and say, well, give me a CBC, tell me to break it down. They're going to give you eosinophil, basophil numbers, and all these. So lymphocytes, monocytes, neutrophils, basophils, eosinophils, and you can actually make diagnostic criteria out of using, you've got a bunch of eosinophils and a 50-year-old lady, does she have like rheumatoid arthritis or something, right? They tell you a lot. I do this all the time, right? I take labs, well now about every couple of months, but so my leukocytes are non-existent on the labs almost, because they give me stuff that keeps them like that. Connected, but yeah, I'm digressing again. Connective tissue fibers. We talked a lot, so where we switched here is we're saying, well, those are all the typical cells you find in connective tissue. That's what we just covered. We said there's cells, but there's a lot more of the ground substance surrounding them, and inside of that ground substance we also have protein fibers, or what we call connective tissue fibers. And there's three different types. You have collagen, you have elastic fibers, and then reticular fibers. And what we're going to pay attention to is how much of each of these, because all three of these are generally in connective tissue, no matter where you find it. But the amount of each one's going to vary. And what we're going to see is that if you have a bunch of collagen, that connective tissue is going to be a lot stronger than a tissue that just has some more reticular fibers. So I'm going to show you that the fibers make up the consistency of that connective tissue. So collagen is found everywhere in the body. They use the analogy, I didn't make this up, of like a rope. Okay? Because it's inelastic. A rope, for the most part, is inelastic. And it's very strong, but it's flexible. Well, so is collagen. But collagen, I love it, has a tensile strength greater than steel. Pound per pound, I don't know how they figured that out, but that's what they say. It's very strong, that's all we need to know. And collagen fibers will be arranged in these parallel kind of bundles. So once again, like, if you ever seen them make a rope's not one solid piece. They weave smaller ones, they weave larger ones, until you get that rope. So we find collagen everywhere. It's the most abundant protein in the body. And when you look at proteins, a large amount of that is going to be collagen. Elastic fibers are made of what's called elastin and fibrillin that combine. And so all of these white lines are elastic fibers. And we're going to find elastic fibers in greater numbers of connective tissue in areas like the skin. Right? We can stretch our skin. Blood vessels, walls. You have to expand the lungs. You probably only need to throw lungs in there, because once you throw lungs, people understand the lungs have to expand. So you need an elastic tissue. Well, then you have to define out and go, well, what's elastic tissue? Elastic tissue is a tissue type that has the ability to be stretched. But being stretched is not enough. It must be able to return to its starting weight. So how far can you stretch it? And that's the threshold limit. So here is my first fancy graphic of the semester, and it's high speed, right? And it's elastic tissue. At some point, that was a good idea to me. And I'll leave it in there for reference, in case you don't understand how elastic tissue returns to its starting weight. I have a lot of high-speed graphics just like that coming up, scattered throughout. I'm not going to update it. I like that. It gives me something to joke about. Reticular fibers. Anytime you hear reticular fibers, I want you to think of the spleen or a lymph node. I'm going to give you others, areas we find these. Reticular fibers are very, very fine bundles of collagen. They are collagen, but they're very fine. They're not strong like true collagen fibers. And they branch. And so if you were to look at areas like blood vessels, areolar connective tissue, adipose, smooth muscle, you're going to see that they have some of these reticular fibers in them. The reason I say it's in the bottom line, it's part of the basement membrane. These are all just generalities, and I'm trying to help you separate where we find like collagen mostly, where we find reticular, where we find elastic. So elastic, we find it mainly in the lungs. But what did I start off with saying? Is collagen, elastic, and reticular fibers are found in all connective tissue. But if you say it's a collagen type tissue, it's going to have a lot more collagen. It may have a minute amount of reticulum. So pay attention and say, well, then what do you mean? Okay, the reason I use spleen and lymph nodes is because those are areas that we probably understand sequester or trap things like bacteria, blood vessels, old blood vessels. And we know the spleen does that. Well, the lungs do that. We look at different, the lungs. The lymph nodes do that. Catch bacteria and things. So if you were to look at a lymph node or the spleen, let's use the spleen. I'll just draw me a. Okay, let's redo that. Let's draw it more like it sits right on it. Here's our spleen. Inside of that spleen, reticular fibers form the stroma. And it's kind of cross-hatched like this. Okay, I always use the same bad joke here, so let's just go ahead and get it over with. Is if you think of cross-hatch, anybody ever seen the better part is an SOS pattern? Right? You ever seen that green, sometimes green, and it's like steel wool? You know what steel wool is, SOS pattern. It's kind of meshed. That's what reticular fibers kind of look like, the stroma of this spleen. And as things go through it, the bad joke I always make is, you know, like people that stuff like steel wool down in their crack pipe so it catches the particles they don't want. I mean, I've never done that, but I've seen it in the movies. I mean, I've done a lot of things in life, but that's not one of them. To think of filtering, like blood vessels that are old get trapped by the spleen. Bacteria get trapped by the lymph nodes. Picture that having to go through that measurement. Alright, and then we get to a harder slide. It looks like, wow, we still got a lot to go through, right? Most of the mature connective tissue on the right side of this, right? We're going to look at a lot of in block 2. But these are classifications for connective tissue. So as we work through these, I promise you, it won't be as challenging as this slide makes it appear. So when we look at, and we're not going to cover bone and liquid because, and cartilage, all of these we're really going to cover under block 12. Cartilage and bone. Liquid connective tissue, guess where that's going to be covered? A&P II. He does circulation. So that would be covered there. So really it's not as hard as we see. We come back over to the other side, and the first area is embryonic connective tissue. Well, we already know that mesenchyme is the main embryonic connective tissue. This is the point where somebody goes, well, wait, Mr. Wright, you said all connective tissues are derived from mesenchyme. They are. But we always come back in medicine and go, there's an exception here. There's an exception. But it's easier to learn it the right way, or the most asked way first. And then come back and say, yeah, but when you're a fetus and you're in the uterus, what do you need connected to you? The umbilical cord. And in the umbilical cord we find mucus connective tissue. But that's the only time we ever see it. Right? And if you want to like nail it down and say, well, wait, is mesenchyme still for all cells? Yes. The fetus is developing. It's mesenchymal cells. It's not even part of the umbilical cord. It's connected. You see what I mean? You can split hairs if you want to. All right. Then mature connective tissue is loose or dense. Loose connective tissue types are going to include areolar, adipose tissues, and then reticular connective tissues. And then when we look at dense connective tissues, we're going to see that there is dense regular and dense irregular. We don't want to make this too easy. I'm joking. You know, y'all are starting to drift on me like, when's this class going to end today? I didn't see that until just now, so that's good. Y'all are doing great. Dense regular, dense irregular are elastic connective tissues. So here's the embryonic. Embryonic connective tissue, I already said all this. Primarily in the embryo, right? It's going to make up mesenchyme or mucus connective tissue. Mesenchyme, when you look at it, has a lot of irregularly shaped cells. It has a kind of semi-fluid ground substance and some reticular fibers. So it's not real well defined. But the cells in mesenchyme are pluripotent. Pluripotent is just like you hear in the news. What's the word in the news for pluripotent cells? Stem cells. Right? They can develop into many different types of cells. Not all cells can do that, right? But mesenchymal cells can, so they're pluripotent. Or else they wouldn't be able to develop every type of connective tissue. Located along the bones, the embryo, under the skin. Great, it's everywhere in the embryo. Mucus connective tissue is also called Wharton's jelly, and it has real widely scattered fibroblasts, more of a viscous jelly type. So think of mucus connective tissue as much thicker than mesenchyme, right? It has viscous jelly ground substance and a few more collagen fibers in it. And if you've looked at an umbilical cord before, it's inside of the womb, baby's moving around in there. You can't have that kink, right? Or you cut off the blood supply to the baby, perfusion, or baby's head's pushing against it. So it resists, has high turgor, meaning it resists compression, whether you try to bend it or put a head against it. But it can compress on that. But the other thing, if you want to know the consistency, if you've ever had a child and you got to cut the umbilical cord, it's hard to describe. It's like a wet eraser to me, or like wet, half-cooked pasta. I don't know. It's tougher than I thought. Because I knew the scissors were sharp. I thought I'd just go right through it. You don't really, I'm kidding, you don't nip your way through it.
It's like octopus, I feel like.
There you go. That's a great, everyone's ever said that. That's a great example, like an octopus. Like I have people in the room are going, I don't know what they're talking about. I've never even seen an octopus in real life. Hey. You believe that stuff. Alright, I know we still have 5 minutes, but you know, we're obviously not going to finish the end of these. We got plenty of time tomorrow, and as I walk out of here tomorrow, we'll finish probably, but I'll stop here so we can do all these at once rather than having to recap again tomorrow. We'll talk about the mature connective tissue types, and that takes us to the end of the material, which, what is it, 270, so we're almost there. So tomorrow, we'll go over and finish those. and then I'll give you the rest of the time by yourselves, or however you wanna manage the time to, do the practice test. I'll talk to you about that. But I'll open the practice test tomorrow for you. It's just another way to gauge your study. You don't have to do it tomorrow. Right? Whatever you want to do. I'm saying it that way because I'm not going to be here at that point. Okay? Unless you have questions or something, I'll stay around after we finish the lecture. But then that second hour is going to be officially open your practice test, so you can do that. If you don't do it tomorrow, that's great. Because me personally, I would probably do it closer to taking A&P. I'd do it next weekend, right? To see where I'm at. Because I want to know after I study, or actually I wouldn't wait till next week. I took it Sunday night and I realized that I didn't pay attention to a lot of little details, and so I was up all night Sunday night trying to catch up. Don't do that. I know I've said it a lot, but I've seen a lot of people go through this program. I've been around here a long time. I saw a lot of students when I was here. I'm going to tell you, you gain, I know they said this, but I'm telling you because I'm hoping I have a little more weight. I used to get up and study. I would get up, go to class, I would come back, study. I'd study 6 hours a night. I mean, it was crazy. But from 6 to 12, I would eat for 30 minutes with my family for dinner. But from 6 to 12, generally every day of the week, and Saturday and Sunday is probably longer. But what I'm saying, I'm trying to develop you an attitude again. I would go from 6 to 12, studying every night. Why do I say 12? How do you know when to stop studying? At 12. For me. At 12, I would make a big production, whatever, because I was reading books then, we weren't doing all computers. And so as I'm reading through current, when I saw it was 12, I would take the book, no matter where I was at in my study, and I would slam it. And I would get up, I would go brush my teeth, use the bathroom, and go to bed. I would sleep 12 to 6. I still do that. I can still sleep 12 to 6. I would do that so that, let's say it's the night before a test. What do people like to do the night before a test? My whole point of this, what I was starting out with, is you will go down in flames if you stay up all damn night studying. I don't care what, you're not getting any more. You're not processing that material, and you're probably screwing with what you've already learned. You're confusing yourself. So I learned to do that, and I would slam that book on night before a test, and I would look at some things like lists and things, but the overall general knowledge on test mornings, I like to get up out of my bed, eat breakfast, walk up here. I wouldn't talk to anybody about testing. I'd talk to you about your kids, whatever, but I don't want to talk about the test. Because I want to hit that door going, I started out the first day with this. I went to the cage. Y'all get that analogy? I put in the swings to do good in the game. In other words, I put in all the effort that I know to do for this test. So when I hit that door, I'm going to be confident in myself. Am I confident I'm going to pass? No. How can I be? I haven't seen the test yet. Am I confident that I did everything I know to do to prepare myself for that moment? Yes, I'm confident in that. That confidence for me over time in PA school developed where when I slammed that book, I would say, I know all that I'm physically going to know before tomorrow. And I would come here and take it. And I stand here today, so now don't do that if you don't know what I mean. But don't stay up all, I'm sorry, I just ranted for your 5 minutes. And I was going to let y'all know, don't stay up all night. I've seen too many people come in and bomb the test because of that. It doesn't help you. All right, listen. Y'all have fun.